Welcome to my representation. I am Ha, a student at Hanoi University of Science and Technology, currently working under the guidance of Dr. Hoàng Hải Trân. I am truly grateful for the opportunity to be part of Advanced Computing and Analytics Conference 2023. Today, I would like to present our work on deep instructive transfer learning approach for network attack detection. Co-author of this paper are Dr. Văn Thiệu Vũ and Dr. Đình Minh Vũ. Content of this article are a brief introduction to the topic, system model, simulation results, conclusion, and future plan, followed by the references. In recent years, we are witnessing a significant surge in cyber attacks attributed to the rapid advancement of cutting-edge computing and network technology. According to cybersecurity venture, by the year 2021, cybercrime was projected to cost up to $6 trillion annually. Startlingly, recent data from MasterCard reveals that 66% of small and medium-sized businesses experienced at least one cyber incident in the past 2 years. Furthermore, an alarm statistics show that 1 out of every 181 emails in delivery contains malicious content. The threats of DOS and DDoS attacks continue to loom large over many corporations and industry, persisting as a crisis that demands our immediate attention. It is evident that safeguarding our digital landscape has never been more crucial. We must proactively adapt and implement robust cybersecurity measures to protect ourselves, our businesses, and our community from these threats. By leveraging the power of machine learning and deep learning techniques for network intrusion detection system offers significant advantages in today's complex and ever-evolving cybersecurity landscape. Machine learning-based NIDS can efficiently analyze vast amounts of network traffic and detect anomalous patterns that may indicate potential security threats. Machine learning enables the NIDS to learn from historical data and adapt to new attack vectors, making it highly effective in identifying both known and previous unseen threats. With continuous learning and improvement, the system becomes more accurate over time, reducing false positives and enhancing the overall security posture of the network. In this article, we implement the diagram of transfer learning to discern anomalous instructions and meticulously showcase prowess across diverse datasets, seamlessly assimilating novel knowledge with remarkable efficiency. The proposed model described in the figure has following objectives. At first, the real network traffic is going to label to construct target data by auto-labeling tools. And then target and base dataset are passed through preprocessing steps to generate preprocessed target and base training testing data as input for transfer learning model. Finally, in the transfer learning stage, build a full CNN transfer learning model, also referenced as classification model. We'll delve into the nitty-gritty details of each component. The first component is auto-labeling. Suricata monitors real-time network traffic. When a packet matches predefined route sets, Suricata saves it into a PCAP files. This file is then passed to CIC flow methods, which generates a CSV file containing 84 features. The next component is preprocessing. The preprocessing stage of our proposed model involves missing value patching. This involves replace missing value with the mean, median, maximum values, or even a constant value. The processing of digitalizing convert character data such as prototype, service, flag into numeric form. One highly effective technique for achieving this is through the one-hot encoding method. After digitalization, it's crucial to ensure that our data is in a consistent and standardized format. By applying technique min-max scaler, we bring our data into a standardized range. The final component is transfer learning. After undergoing the preprocessing step, the base dataset and target dataset are divided into base training and target training sets for model training, as well as base testing and target testing sets for evaluation. Transfer learning model involves a two-stage learning process, state 1 learning and state 2 learning. State 1 learning trains a CNN model, or we call it CNNB, and a fully connected net on the base dataset. This aimed to extract generic traffic pattern to support learning of the target dataset. After CNN-B is trained, the old fully connected net is removed, and the second CNN model, or CNN-T, and a new fully connected are added to form the whole CNN transfer learning model for the state 2. In state 2 learning, CNN-B is fixed, and only CNN-T and a fully connected net are trained on the target dataset. It should be noted that a threshold must be set in state 2 learning to stop the retraining process when achieving a certain value of evaluation metric on target dataset. After completing state 2 of learning, the model was evaluated on the testing dataset of CIC EDAT 2017 Wednesday and Suricata dataset. Table 1 shows the statistic of CIC EDAT 2017 Wednesday and Suricata generated dataset. We divided the dataset into 80% for training and 20% left for testing. We used 3 key evaluation metrics: accuracy, detection rate, and false negative rate. Accuracy used to measure the overall accuracy of the model's prediction. Accuracy can be represented as Formula 1. The detection rate focuses on the model's ability to correctly identify positive instances among the entirety of the actual positive instances. Detection rate can be calculated by using Formula 2. False negative rate highlights the model's tendency to incorrectly predict negative outcomes when they are actually positive. Formula 3 represents false negative rate. The result, as depicted in the figure 1 and 2, demonstrate that the transfer learning model exhibits a high level of accuracy in correctly classifying majority of the sample within the CIC EDAT 2017 Wednesday dataset. Moreover, a closer examination of figure 3 and 4 in the confusion matrix reveals a notable increase in detections of packets with new label HTTP flood dots after the transfer learning state. This finding indicates that the model's ability to detect this particular types of attack has been significantly improved, showcase the effectiveness of transfer learning approach. When comparing with CNN model, the CNN transfer learning model showcase markedly superior results when dealing with new label. The CNN transfer learning model achieved a substantially higher detection rate of 64.57% and an improved accuracy of 42.16%. Moreover, when assessing the performance of both models on the CIC EDAT 2017 Wednesday dataset, the CNN transfer learning model once again outperformed the CNN model. There are 2 main contributions in this article. The first one is the adoption of Suricata as a primary tool for intrusion detection and prevention. This departure from the conventional use of snort brings several advantages to the forefront. Suricata's multi-threaded architecture and high-performance capability enable more efficient processing of network traffic, ultimately leading to improved detection accuracy and reduced false positives. The study also introduced a substantially enriched data source. This diversification of data source empowered the model to effectively adapt to previous unseen attacks patterns, thereby enhancing its overall robustness and applicability across different domains. The model's ability to maintain its performance across diverse data sources is not only validates the robustness of our approach, but also highlights its potential for widespread adoption in real-world scenarios. In conclusion, the presented model has demonstrated its ability to retain both new and old knowledge after the transfer learning process, showcasing its effectiveness in knowledge transfer across different domains. Moreover, the model capacity for generalization with various types of data further highlight its versatility and robustness. However, it is important to acknowledge certain limitations. Specifically, the imbalance in data within the base dataset has led to lower detection rate for minority labels. This imbalance issue is an area that warrants further attention in future research endeavors. Strategies such as data augmentation or specialized technique for handling imbalanced dataset should be explored to address this challenge. Additionally, the model's performance could be further fine-tuned through continued refinement of hyperparameters and exploration for advanced transfer learning methodology. The utilization of Suricata as a chosen tool has effectively showcased its advantageous feature. Its robust features and efficient processing capability has significantly enhanced the model's effectiveness. Our work contributes to the ongoing advancement of transfer learning techniques in the field. The model's adaptability and proficiency in diverse settings are a statement to the broader impact it can have on the enhancing the security measure in contemporary network environment. I would like to thank the organizing committees for providing me a wonderful opportunity to present my article in this conference. I really appreciate and answer the query if you have any. Thank you.